Lesson 3 is called Similarity and Transformations. Now, Lesson 3 is very similar to Lesson 1. If you remember back to Lesson 1 talked about congruence and transformations, how we use the different transformations to prove congruence. Okay, that's what Lesson 3 is on. Lesson 3 is using transformations again to prove similarity this time, not congruence. Okay, so let's take a look at what we've got. Let's get your vocabulary startup. Complete the graphic organizer. Consider each word on the rating scale and place a check in the appropriate column next to the word. If you do not know the meaning of the word, find the meaning in the glossary or on the internet. So what you need to do is you need to go through, and here's your first word, dilation. Do you know it well? Have you seen it or heard it, or do you have no clue? So they just want you to do these 3 vocabulary words, and they want you to check it wherever you feel that you fit. So if you have no idea what a similar figure is, you put no clue. And then we'll talk about the meaning of those 3 words. Okay, so pause the video right now and take a few moments to do this. Now, I think we have discussed all 3 of these words. We've definitely discussed dilation. Okay, so hopefully you were able to check know it well. But let's take a look and see what you had for your definition. Okay. It's an enlargement or a reduction of a figure, or you take a figure and you make it bigger, or you make it smaller. Okay, that's what a dilation is. Scale factor. Scale factor is the ratio of the length of a side on a scale model to the same side of the original object. Now, you don't have to have that exact definition down. Your scale factor tells you how big or how small your dilation is going to be. Okay, it's the number value. Scale factor of 2, a scale factor of 1. Okay, that's what your scale factor is. Now, we've also talked about what similar figures are. Let's take a look at the definition of similar figures. 2 figures that are the same shape but have different sizes. That's what a similar figure is, okay? That's different than congruent. Congruent means same shape, same size. Similar can mean 2 figures that are the same shape but different sizes. Let's take a look. The first part, what we're going to do is we're just going to identify similarity. We're going to say, are these 2 figures similar? And we're going to do that by using transformations again. Let's look at example 1 here. Determine if the 2 triangles are similar by using transformations. So we want to look at triangle EDF and triangle HGI. Okay, and we want to see if they're similar. Well, what we can do is let's do a translation first. Let's translate triangle EDF and let's put it on top of HGI. Now, obviously they're different sizes, but let's pretend, let's move this triangle DEF, let's move D right onto point G. Okay? Now, what we did there is we did a translation. We translated it 2 over and 5, or 2 down and 5 over, so that D and G are in the same spot. Here's how you prove, now that we've done that before. Step 2 is how you prove the dilation part, okay? Because we are going from a smaller figure to a bigger figure, so that is a dilation. What you have to do is you have to take a look at the corresponding sides, okay? So let's look at, they're comparing HG, which is this length right here, and ED. Those are the corresponding sides. So if we take a look, the length of HG is 8. The length of ED is 4. So 8 over 4 reduces to 2. Okay? Or 2 over 1, same thing. Now let's look at the other 2 corresponding sides. GI corresponds to DF. GI has a length of 6. DF has a length of 3. Or, when you reduce it, 2 over 1. And then you can do the same sides, you can do the diagonals as well. HI has a length of 10, FE has a length of 5, and again we have a ratio of 2 to 1. So because all of these lengths, all of these ratios are the same, it is a dilation. Okay, and we can say the two triangles are similar because we used a dilation and a translation. Just like this is just like lesson 1, except now we're throwing in dilations. Okay? Let's look at example 2. Determine if two rectangles are similar by transformations. Okay, this one is going to involve a rotation. So what we can do, let's take this shape right here, and we're going to rotate this smaller rectangle, and we're going to rotate it around point W. Point W is going to stay the same. It's like we're putting a pin right there in W. And we're going to rotate it so that it's oriented the same way. Okay? So you can see down here, do you see what they've done? They've taken this shape, they've held point W right where it is, and they just rotated that shape 90 degrees. Okay? So once we do that, we can compare corresponding sides. So they're saying WT, okay, here's WT, that corresponds with XY. Okay, here's WT, and it's going to correspond with XY. XY has a length of 7. WT has a length of 5. Okay, now let's compare another side. Let's do TU and YZ. Okay, here's YZ. That has a length of 4. TU has a length of 3. Do you see how these ratios are different? Because these ratios are different, that means that they're not similar. Okay, and that therefore the scale factor isn't the same. Okay, this had a different scale factor than this, therefore the triangles or the rectangles are not similar. So you're looking for consistent ratios. Okay, so let's do this. Why don't you try the two got it problems? Okay, you're looking for ratios. So go ahead and pause the video and try these two. Alright, let's take a look at A. What we would have to do first is we would have to reflect this. So we're going to reflect it so that it has the same orientation, so it's facing the same way. When we do that, okay, we can compare PQ, this line, this line right here, and ST. They are corresponding sides. So PQ has a length of 6, ST has a length of 3. Well, 6 over 3 reduces to 2 over 1. Okay? Now, if they are to be similar, let's take another side, okay, and see if we get a ratio of 2 over 1. Okay? Let's look at QR. So here we have QR. That has a length of 10. TU has a length of 5. Well, look, we end up with the same ratios. 2 over 1, 2 over 1. Therefore, they're going to be similar. Okay? So our answer, what transformations did we have to do? Well, we had to do a reflection first. And then we did a dilation. Okay? Now let's take a look at B. Same thing. This one would involve a translation. We could just slide this one down so that H and D were on the same point. Okay? And let's look at our dilations here. Let's look at some ratios. Let's take EF and compare it to its corresponding side AB. Okay? Well, EF has a distance or a length of 2. AB has a length of 3. So here's the ratio that we're looking for. Okay? If we find one side that doesn't have a ratio of 2/3, it's not similar. Let's check EF and H and AD. So here's EH, that has a length of 4. AD right here has a length of 5. Well, again, if you take a look, we have 2/3 and we have 4/5. They are not equal. The ratios aren't equal. Okay, they don't have the same scale factor. Therefore, these two figures are not similar. Okay, they have to have the same ratio. Okay. Now, what they're going to do next, they're going to talk about using the scale factor. That was using ratios. Now they want us to use scale factors. And if you take a look at this, this is something that we already know. This is a review. If your scale factor is between 0 and 1, it's going to make the figure smaller. If it's equal to 1, it stays the same. If it's greater than 1, it's going to be larger. It's an enlargement. Okay? Let's take a look at the example here. Ken enlarges the photo shown by a scale factor of 2 from his web page. Then he enlarges the web page by a scale factor of 1.5. So we're doing two dilations here. So what you need to know is the original picture is, let's say this is the original picture, 2 by 3. So since the first enlargement is a scale factor of 1.5, you've got to take 2 and 3 and you've got to multiply it. Oh, sorry. Let's go back. Your first scale factor is actually 2. Sorry, my bad. Scale factor of 2. So you need to take 2 times 2 and you need to take 3 times 2. So now your new photo is not 2 and 3. It's going to be 4 and 6, 4 by 6. Then he does another enlargement, and that is a scale factor by 1.5. So now you have to take 4 times 1.5 and 6 times 1.5. So now your final picture now becomes 6 by 9. So really all this one is just a double dilation. Okay? Why don't you try this got it problem? An art show offers different size prints of the same painting. The original print measures 24 by 30 centimeters. So I went ahead and helped you out here and I drew a picture of this painting. Okay. 24 by 30. Okay. The printer enlarges the original scale factor, or the original picture, by a scale factor of 1.5. Then enlarges it again by a scale factor of 3. What are the dimensions of the largest print? And are both enlarged prints similar to the original? So pause the video right now and work this problem out. So let's see, what is going to be our ending dimensions for this print? And this, by the way, is a portrait of Gavin right here. So if we do a scale factor of 1.5 first, okay, we've got to go 30 times 1.5 and 24 times 1.5. And what that does is it gives us 45 and 36. So there's after the first dilation. Okay? Then what we have to do is use a scale factor of 3. So we need to take 45 and 36 and multiply it by 3. And when you multiply this by 3, you end up with 135 by 108. So your final enlargement is going to be 135 centimeters by 108 centimeters. And it wants to know, are both of the enlarged prints similar to the original? Yes, they are, because we use the same ratio or the same scale factor each time with each picture. Okay, so we did both of these by 1.5, then we did both sides by 3. And because these are the same ratio or the same scale factor on this one, and then 3 and 3 here, therefore it makes it similar. Okay? So what I need for you guys to do, go ahead and do the guided practice, and we'll see how we end up tomorrow.